In mathematics, a root of unity, occasionally called a Moivre number, is any complex number that gives 1 when raised to some positive integer power n. Roots of unity are used in many branches of mathematics, and are especially important in number theory, the theory of group characters, and the discrete Fourier transform. In field theory and ring theory, the notion of root of unity also applies to any ring with a multiplicative identity element. Any algebraically closed field has exactly n nth roots of unity, if n is not divisible by the characteristic of the field. General definition: an nth root of unity, where n is a positive integer, is a number z satisfying the equation traditionally. Z is assumed to be a complex number, and subsequent sections of this article will comply with this usage. Generally, ZR can be considered for any field R, or even for a unital ring. In this general formulation, an nth root of unity is just an element of the group of units of order n. Interesting cases are finite fields and modular arithmetics, for which the article root of unity modulo n contains some information. An nth root of unity is primitive if it is not a kth root of unity for some smaller k. Elementary facts: every nth root of unity z is a primitive th root of unity for some r where 1 or n. If z1 equals 1, then z is a primitive first root of unity, otherwise if z2 equals 1, then z is a primitive second root of unity, otherwise. And by assumption there must be a 1 at or before the nth term in the sequence. If z is an nth root of unity and a b, then r equals zb. By the definition of congruence, r equals b plus naught for some integer k. But then, therefore, given a powers r of z, it can be assumed that 1 or n. This is often convenient. Any integer power of an nth root of unity is also an nth root of unity. Here k may be negative. In particular, the reciprocal of an nth root of unity is its complex conjugate, and is also an nth root of unity. Let z be a primitive nth root of unity. Then the powers z, z2, zinc minus 1, zinc equals z0 equals 1 are all distinct. Assume the contrary, that r equals zb where 1 are less than bn. Then zb minus r equals 1. But 0 less than b minus a less than n, which contradicts z being primitive. Since an nth degree polynomial equation can only have n distinct roots, this implies that the powers of a primitive root z, z2, zinc minus 1, zinc equals z0 equals 1 are in fact all of the nth roots of unity. From the preceding facts it follows that if z is a primitive nth root of unity, if z is not primitive there is only one implication. An example showing that the converse implication is false is given by: let z be a primitive nth root of unity and let k be a positive integer. From the above discussion, zk is a primitive th root of unity for some a. Now if zka equals 1, k must be a multiple of n. The smallest number that is divisible by both n and k is their least common multiple, denoted by LCM. It is related to their greatest common divisor, GCD, by the formula, i.e. Therefore, zk is a primitive th root of unity where thus, if k and n are coprime, zk is also a primitive nth root of unity, and therefore there are 5 distinct primitive nth roots of unity. In other words, if R is the set of all nth roots of unity and P is the set of primitive ones, R is a disjoint union of the P, where the notation means that D goes through all the divisors of n, including 1 and n. Since the cardinality of R is n, and that of P is phi, this demonstrates the classical formula examples. The Moivre's formula, which is valid for all real x and integers n, is setting x equals 2 pi, n gives a primitive nth root of unity. But for k equals 1, 2, n minus 1. This formula shows that on the complex plane the nth roots of unity are at the vertices of a regular n-sided polygon inscribed in the unit circle, with one vertex at 1. This geometric fact accounts for the term cyclotomic in such phrases as cyclotomic field and cyclotomic polynomial. It is from the Greek roots cyclo plus tomos. Euler's formula, which is valid for all real x, can be used to put the formula for the nth roots of unity into the form it follows from the discussion in the previous section that this is a primitive nth root if and only if the fraction k, n is in lowest terms, i.e., that k and n are co-prime. The roots of unity are trigonometric numbers and are, by definition, the roots of a polynomial equation and are thus algebraic numbers. In fact, Galois theory can be used to show that they may be expressed as expressions involving integers and the operations of addition, subtraction, multiplication, division, and the extraction of roots. The equation z1 equals 1 obviously has only one solution, plus 1, which is therefore the only primitive first root of unity. It is a non-primitive second, third, fourth root of unity. The equation z2 equals 1 has two solutions, plus 1 and minus 1. Plus 1 is the primitive first root of unity, leaving minus 1 as the only primitive second root of unity. It is a non-primitive fourth, sixth, eighth root of unity. The only real roots of unity are plus or minus 1, all the others are non-real complex numbers, as can be seen from de Moivre's formula or the figures. The third roots satisfy the equation z3 minus 1 equals 0, the non-principal root plus the first of may be factored out, giving E equals 0. Therefore, the primitive cube roots of unity are the roots of a quadratic equation. The two primitive fourth roots of unity are the two square roots of the primitive square root of unity, minus 1. The four primitive fifth roots of unity are the two primitive sixth roots of unity are the negatives of the two primitive cube roots. Gauss observed that if a primitive nth root of unity can be expressed using only square roots, then it is possible to construct the regular n-gon using only ruler and compass, and that if the root of unity requires third or fourth or higher radicals, the regular polygon cannot be constructed. The seventh roots of unity are the first, that require cube roots. Note that the real part and imaginary part are both real numbers, but complex numbers are buried in the expressions. They cannot be removed. See Casuis irreducibilis for details. One of the primitive seventh roots of unity is where omega and omega-2 are the primitive cube roots of unity exp and exp. The four primitive eighth roots of unity are plus or minus the square roots of the primitive fourth roots, plus or minus I. One of them is. See heptadecagon for the real part of a 17th root of unity. Periodicity. If Z is a primitive nth root of unity, then the sequence of powers Z-1, Z0, Z1 is n-periodic, and the n sequences of powers Sk, Zk, Zk0, Zk1, for k equals 1, n are all n-periodic. E equals Zkj. Furthermore, the set S1, Sn of these sequences is a basis of the linear space of all n-periodic sequences. This means that in any n-periodic sequence of complex numbers, x-1, x0, x1 can be expressed as a linear combination of powers of a primitive nth root of unity. For some complex numbers x1, xn and every integer j, this is a form of Fourier analysis. If j is a time variable, then k is a frequency and xk is a complex amplitude. Choosing for the primitive nth root of unity z equals e2 pi I, n equals cos plus I sin allows xj to be expressed as a linear combination of cos and sin. xj equals k at cos plus kb k sin. This is a discrete Fourier transform. Summation. Let senior be the sum of all the nth roots of unity, primitive or not. Then for n equals 1 there is nothing to prove. For n greater than 1, it is intuitively obvious from the symmetry of the roots in the complex plane. For a rigorous proof, let Z be a primitive nth root of unity. then the set of all roots is given by zk, k equals 0, 1, n-1, and their sum is given by the formula for a geometric series. Let Sp be the sum of all the primitive nth roots of unity. Then where mu is the Mobius function. In the section Elementary Facts, it was shown that if R is the set of all nth roots of unity and P is the set of primitive ones, R is a disjoint union of the P. This implies applying the Mobius inversion formula gives in this formula, if d less than n, then senior equals 0, and for the d equals n, senior equals 1. Therefore, Sp equals mu. This is the special case Cn of Ramanujan's sum Cn, defined as the sum of the south powers of the primitive nth roots of unity. Orthogonality. From the summation formula follows an orthogonality relationship. For j equals 1, n and j equals 1, n where delta is the Kronecker delta and z is any primitive nth root of unity. The n times n matrix U whose th entry is defines a discrete Fourier transform. Computing the inverse transformation using Gaussian elimination requires O operations. However, it follows from the orthogonality that U is unitary, that is, and thus the inverse of U is simply the complex conjugate. The straightforward application of U or its inverse to a given vector requires O operations. The fast Fourier transform algorithms reduces the number of operations further to O. Cyclotomic polynomials. The zeros of the polynomial are precisely the nth roots of unity, each with multiplicity 1. The nth cyclotomic polynomial is defined by the fact that its zeros are precisely the primitive nth roots of unity, each with multiplicity 1, where z1, z2, z3, z-phi are the primitive nth roots of unity, and phi is Euler's totient function. The polynomial phi n has integer coefficients and is an irreducible polynomial over the rational numbers. The case of prime n, which is easier than the general assertion, follows by applying Eisenstein's criterion to the polynomial and expanding via the binomial theorem. Every nth root of unity is a primitive dth root of unity for exactly one positive divisor d of n. This implies that this formula represents the factorization of the polynomials inc-1 into irreducible factors. z1-1 equals z-1, z2-1 equals z3-1 equals z4-1 equals z5-1 equals z6-1 equals z7-1 equals. Applying Mobius inversion to the formula gives where mu is the Mobius function. So the first few cyclotomic polynomials are phi1 equals z-1, phi2 equals -1 equals z plus 1, phi3 equals -1 equals z2 plus z plus 1, phi4 equals -1 equals z2 plus 1, phi5 equals -1 equals z4 plus z3 plus z2 plus z plus 1, phi6 equals -1 equals z2 minus z plus 1, phi7 equals -1 equals z6 plus z5 plus z4 plus z3 plus z2 plus z plus 1. If P is a prime number, then all the pth roots of unity except one are primitive pth roots, and we have substituting any positive integer 2 for z. This sum becomes a base z repunit. Thus a necessary condition for a repunit to be prime is that its length be prime. Note that, contrary to first appearances, not all coefficients of all cyclotomic polynomials are 0, 1, or -1. The first exception is phi 105. It is not a surprise it takes this long to get an example, because the behavior of the coefficients depends not so much on n as on how many odd prime factors appear in n. More precisely, it can be shown that if n has one or two odd prime factors, then the nth cyclotomic polynomial only has coefficients 0, 1 or -1. Thus the first conceivable n for which there could be a coefficient besides 0, 1, or -1 is a product of the three smallest odd primes. and that is 357 equals 105. This by itself doesn't prove the 105th polynomial has another coefficient, but does show it is the first one which even has a chance of working. A theorem of Schur says that there are cyclotomic polynomials with coefficients arbitrarily large in absolute value. In particular, if n equals p1, p2, pt, where p1 less than p2 less than pt are odd primes, p1 plus p2 greater than pt, and t is odd, then 1 minus t occurs as a coefficient in the nth cyclotomic polynomial. Many restrictions are known about the values that cyclotomic polynomials can assume at integer values. For example, if p is prime and d phi p, then either d1 or d0. Cyclotomic polynomials are solvable in radicals, as roots of unity are themselves radicals. Moreover, there exist more informative radical expressions for nth roots of unity with the additional property that every value of the expression obtained by choosing values of the radicals is a primitive nth root of unity. This was already shown by Gauss in 1797. Efficient algorithms exist for calculating such expressions. Cyclic groups. The nth roots of unity form under multiplication a cyclic group of order n, and in fact these groups comprise all of the finite subgroups of the multiplicative group of the complex number field. A generator for this cyclic group is a primitive nth root of unity. The nth roots of unity form an irreducible representation of any cyclic group of order n. The orthogonality relationship also follows from group theoretic principles as described in character group. The roots of unity appear as entries of the eigenvectors of any circulant matrix, i.e., matrices that are invariant under cyclic shifts, a fact that also follows from group representation theory as a variant of Bloch's theorem. In particular, if a circulant Hermitian matrix is considered, the orthogonality property immediately follows from the usual orthogonality of eigenvectors of Hermitian matrices. Cyclotomic fields. By adjoining a primitive nth root of unity to Q, one obtains the nth cyclotomic field Q. This field contains all nth roots of unity and is the splitting field of the nth cyclotomic polynomial over Q. The field extension Q has degree phi and its Galois group is naturally isomorphic to the multiplicative group of units of the ring Z, Nz. As the Galois group of Q is abelian, this is an abelian extension. Every subfield of a cyclotomic field is an abelian extension of the rationals. It follows that every nth root of unity may be expressed in terms of k-roots, with various k not exceeding phi. In these cases, Galois theory can be written out explicitly in terms of Gaussian periods. This theory from the dispositionis arithmetici of Gauss was published many years before Galois. Conversely, every abelian extension of the rationals is such a subfield of a cyclotomic field. This is the content of a theorem of Kronecker, usually called the Kronecker-Weber theorem on the grounds that Weber completed the proof. Relation to quadratic integers. For n equals 2, both roots of unity 1 and -1 belong to Z. For 3 values of n, the roots of unity are quadratic integers. For n equals 3, 6 they are Eisenstein integers. For n equals 4 they are Gaussian integers. See imaginary unit. For 4 other values of n, the primitive roots of unity are not quadratic integers, but the sum of any root of unity with its complex conjugate is a quadratic integer. For n equals 5, 10, neither of non-real roots of unity is a quadratic integer, but the sum z plus z equals 2 res of each root with its complex conjugate is an element of the ring Z, 1 plus square root 5 halves. For 2 pairs of non-real fifth roots of unity, these sums are inverse golden ratio and minus golden ratio. For n equals 8, for any root of unity z plus z equals to either plus or minus 2, 0, or plus or minus square root 2. For n equals 12, for any root of unity, z plus z equals to either 0, plus or minus 1, plus or minus 2, or plus or minus square root 3.